Yes.
So it is my pleasure to introduce David Blecher from the University of London, not London, Houston, sorry, from the University of Houston. And his talk is Jordan operator algebras and beyond. And please, David, thank you.
Thank you so much. Well, actually, I was born in London. Um,
So,
I'm not currently in London, but I was born there.
but actually,
So
I detect some, some accent from English accent. So maybe that's the thing.
yes. Well, um, thank you. I want to thank the organizers very much for this opportunity to speak here in the seminar. It is a great privilege, and um, I was very much hoping to meet many of you in Canterbury. I guess it was last year, but unfortunately, I was unable to come. Um, but um, yes, so today I'm going to be discussing joint work with Matthew Neal, mostly discussing joint work with Matthew Neal, Antonio, who is here, and Shanshan Su, discussing the class of Jordan operator algebras and their M-ideals. But more generally, for this audience, I would like to pose a question that I think may turn out to be maybe an important question, which is which other non-associative algebras can be treated in the category of operator spaces and operator systems, and which would benefit from this perspective. So, of course, Jordan algebras arose in the context of formalizing quantum mechanics, and it's unnecessary to say to this audience that um, Jordan products make sense in the observables in quantum mechanics, whereas regular products do not. JC star algebras are subspaces of C star algebras which are closed under squares, or equivalently the Jordan product. The adjoint in the C star algebra, and also closed under the norm topology. Um, so in this talk, an operator algebra, respectively, a Jordan operator algebra, is an associative subalgebra of a C-star algebra, or respectively, in the Jordan case, a Jordan subalgebra of a C-star algebra, a subspace closed under squares or Jordan products. And this is an interesting class of operator spaces that have not had a lot of study until now. So on this slide, I just compiled a list of examples. The first class, I'm sorry, I beg your pardon. The first class, of course, are regular operator algebras. Then I mentioned the JC star algebras, which are closed self-adjoint subspaces of C star algebras closed under squares. And then there are various natural constructions, even on associative operator algebras, that will produce Jordan operator algebras in the sense of the previous slide. So, for example, the ranges of various natural classes of contractive projections on operator algebras or Jordan algebras turn out to be Jordan operator algebras. Also, another example. So, in the self-adjoint theory, it's a very important trick is to take the generators of a well-known C-star algebra and then consider the operator system or the Jordan algebra containing those generators. That's a very powerful trick in C-star algebra theory. Then you can also form Jordan operator algebras in JC star triples by fixing an element of the ball and defining bilinear map in this way, for example, and that gives a Jordan operator algebra in the sense of the previous slide. Um, and many such Jordan operator algebras are um, uh, many such Jordan operator algebras, I beg your pardon, are isometrically isomorphic as Jordan algebras, but very different as operator spaces. So I'll just mention some of the recent papers that I and co-authors have worked on in this sense. I noticed that sadly the little panel has disappeared with the pictures of the audience. The danger of that is I have no idea if you guys are still there or if I've done something that has turned off the meeting or something. Is somebody out there?
I'm here.
Yes,
Yeah.
don't
Oh,
worry.
perfect.
We are
Perfect.
we
Okay.
follow you. We follow
Thank
you.
you. Thank you. You can see on the screen sharing that somehow I turned off the picture of the audience. So uh, sorry about that. Okay. Yeah. So let me mention some recent papers of myself and co-authors. So the first one was a paper with grad student Zhenhua Wang in 2018, which laid out the basic theory of these Jordan operator algebras. The second one was a continuation of that with Matt Neal on the non-commutative topology of Jordan operator algebras. Um, so here we showed that Jordan operator algebras are perhaps the most general setting for a full non-commutative topology in the sense of Ackermann, Brown, Peterson, etc. And as modified to not necessarily self-adjoint algebras. The third paper here is a short one that in particular solved an open problem from the first paper at the top of the list. And then in 21, with Matt Neal, we have a paper where we studied surjective isometries between Jordan operator algebras, so Banach-Stone type results, and also contractive projections on operator algebras. Then the next paper is a lengthy survey paper, which continued a large part of that paper, although it's a survey paper, a large part of it was new results, continuing the paper that I just mentioned on contractive projections and expanding some of that. Then in then with another graduate student, Warwick Tepson, we introduced the real version of Jordan operator algebras and began their theory in that paper. And then we come to a pair of papers, one of which I'll be spending most of the time talking about today. The first one with Matt, Antonio, and Shanshan appeared in Raksam. And the second one here was just accepted maybe last week. I think it is just accepted and has already appeared. I guess things happen very quickly after acceptance these days, it seems. So that one just appeared a few days ago. So and then if I have time, I would like to talk about some work in progress with my graduate student Caleb McClure and Mehrdad Kalantar, where with some other topics we discuss some other classes of non-associative algebras motivated by some things in group representation theory. So I should apologize. This is the first time I'm talking about this particular paper. And like any time you do a first-time talk, particular if it's an e-talk, not a live talk, where you can be more free form on a whiteboard or something, there may well be some typos or rough patches, and I may not have had enough coffee. And also feel free to stop me if I use a word without definition, etc. Because of course I'm aware that many people in the seminar um, uh, uh, work on things that are a little distance away from what I'm talking about today, perhaps a little distance away from operator algebras in the sense of this talk. So feel free to stop me at any time. And as I mentioned in the abstract, I think maybe one of the most important things is I would be very interested in other non-associative algebras, which can be treated as operator spaces and systems, and which would benefit from that. Operator spaces and systems have been extremely useful in the study of C-star algebras, and also, and maybe even more so, the study of non-self-adjoint operator algebras. And some of that magic that happens there in the interface between operator spaces and C-star algebras some of that magic should be happening for more non-self-adjoint algebras. So, for example, there are some papers and books, and the book of Angel Rodriguez Palacios and co-authors, which do talk about the matrix norm structure and the operator space structure, and some other people. So feel free to contact me if you have a norm non-associative algebra that might benefit from being an operator space. That would be very interesting. Okay, so section 2, I'm reporting on this work that, as I said, just appeared this week and was accepted last week on M-ideals in operator algebras and Jordan operator algebras. So for those of you who are not familiar with M-ideals, let me begin with the question. Can you recognize the ideals? Those could be left ideals, right ideals, or two-sided ideals in an operator algebra with a condition that only involves the normed linear structure. So what is an M-ideal? An M-ideal is a closed subspace of a Banach space X, such that if you've got n closed balls in the Banach space whose intersection is non-trivial, and each of these balls intersect J, then the intersection of the balls intersect J. So if you think about that condition, it only involves the normed linear structure. Nothing else is needed here to define these M-ideals in a Banach space. So I guess in the next slide, I've repeated the definition and also incorporated the only picture, I think it's the only picture in the famous paper of Elfson and Efros illustrating this definition. So in the first figure, we're looking at the x-axis maybe in R2, say, and we have two balls, and each of them intersects each other, and each of them intersects the x-axis, J, but the intersection of the balls does not intersect the x-axis. And what that is saying is that the x-axis is not an M-ideal in the plane with the Euclidean 2 norm. Whereas if you take the same plane but with the infinity norm, then you can see if you have a bunch of balls, so the balls in the infinity norm look like this. All of the balls intersect each other, and each of them intersects the x-axis, and the intersection of all the balls, which is this shaded area, also then is forced to intersect the x-axis. So that is an M-ideal in L infinity. And indeed, the x-axis is an algebraic ideal in L infinity too, in the two-dimensional L infinity, whereas the two-dimensional Euclidean space with the Hilbertian norm has no non-trivial M-ideals. And then, of course, there are the principal ideals, which often turn out to be a central idempotent or projection in the algebra multiplied by A. So the principal ideals in an algebra A, can you characterize these with a condition involving only the normed linear structure? Oops. Something has gone wrong. I think perhaps I have to stop sharing and try again. So something happened after a certain page. It looks like it is okay on this version. So let me let me try this view. Okay, so okay, that should be good. Let me just fast forward to where I was before. Yes, so the the principal ideals. So often, or we would hope that these principal ideals turn out to be the.
Sorry, we cannot
Oh,
see your slides.
Okay. I beg your pardon. Let me. I think I stopped to screen share. Not enough coffee. I'm sorry about that. Okay. Hopefully that is okay now.
Yes, it's fine.
Okay. Thank you very much. Thank you. So the hope is that these principal ideals would turn out to be the M summands, i.e. the L infinity direct summands. So these are the summands that you can write the whole space as K infinity sum L, or equivalently the ranges of the M projections on A, where the definition of the M projection is that the norm of X is the maximum of PX and I minus PX, which turns out to be equivalent to this condition at the bottom of the slide. So again, purely a condition involving the normed linear structure. Yes. So in the middle of the page here, Elson and Epros showed that these spaces that have this ball property, this property of the intersection of the balls, are exactly the closed subspaces, such that the second perp, which is the second annihilator, or if you like, the weak star closure, the weak star closure in the bidual is an L infinity summand in the sense of the previous slide. And then Elson and Efros, Smith and Ward. So the history of this result is slightly complicated. So Elson announced this result in a paper, but I think the full proof came out a few years later with Smith and Ward. the closed ideals in a complex C-star algebra are exactly the M ideals. The closed M ideals in a JC algebra. So in the actual Elfson Efros paper, they actually don't characterize the closed ideals in a complex C-star algebra, but they do characterize the closed ideals in a JC algebra. And the other case, as I said, appeared formally later in a paper of Smith and Ward. The Another theorem along this line is that the closed ideals in a JB star algebra are in a one-to-one correspondence with the M ideals. But surprisingly, the algebraic characterization of M ideals in real C-star algebras was missing for 50 years, which is a little surprising because the original Elfson and Efros example was in a real C-star algebra. In fact, in a JC algebra. So in the paper that I mentioned from 2024, it was shown that the M ideals in a real C-star algebra are indeed the closed two-sided ideals, and the M ideals in a real JC star algebra are the closed two-sided Jordan ideals. Similarly, for the M ideals in a real JB star algebra. So more recently, we found a shorter proof of the real C star algebra result and the real JC star algebra result that also generalizes to the non-self-adjoint case. And so this result says if you have an approximately unital, so what that means is it has a contractive approximate identity, which you have to say a little bit more about what a contractive approximate identity might mean in a Jordan operator algebra. If I have time, I'll come back and define that in a Jordan operator algebra. But if you have an approximately unital real operator algebra or Jordan operator algebra, the M ideals are exactly the closed two-sided ideals, respectively the closed Jordan ideals, which are also approximately unital in the sense that I was just talking about. And then the M summands in A are the principal ideals, which I was talking about a little while back. They are the ideals AE for a projection E in the multiply algebra, M of A, such that E commutes with all elements in A. So in a Jordan algebra, one has to say a word or two about what it means for elements to commute, but it all makes perfect sense in a Jordan sense, as the next item indicates. So if you have this equation, we simply say that P commutes with X, and if P commutes with all elements of the algebra, we say that P is central. So a corollary is if you have an approximately unital real operator algebra or Jordan algebra and a closed subspace J, then J is an M ideal of A, if and only if J is an M ideal in the unitization, and if and only if the J plus I times J is an M ideal in the complexification. So I'll say a word or two about the complexification a little later, but for now, we'll just leave it a little loose. Exactly what is the complexification and the unitization? So the correspondence in the corollary is not a bijective correspondence onto all of the M ideals or the ideals of the complexification. So a nice example is the continuous functions in the circle that that are fixed by I'm sorry, there's something missing in this equation. There should be an equal to f of t here. So this is actually your canonical real commutative C-star algebra. Every commutative real C-star algebra looks something like this on some space. Here this is appearing on the circle, but every commutative real C-star algebra looks analogous to this for some homeomorphism T of the underlying topological space. And so T here is the circle, and the ideal corresponding to the functions annihilating the upper half circle is not of the form J plus Ij. The ideals of the form J plus Ij are exactly the ideals that are invariant under this automorphism. And then generalizing Elson and Efros's original result. So, like I said, Elson and Efros in the original paper didn't have the case of M ideals in general C-star algebras, but rather the M ideals in JC algebras. And this would be the real case of that the M ideals in a JC algebra, in the self-adjoint part of a real C-star algebra, are exactly the self-adjoint parts of two-sided ideals in A. So I'll mention briefly, because we'll need the next lemma, TROs, or ternary rings of operators, which are subspaces of operators between two Hilbert spaces that if you multiply three elements in Z, with the middle one being, you'd have to take the adjoint of that element. If you multiply those three operators, you remain in Z. Then in the paper from 2024, it's proved that the M ideals in a real TRO are exactly the closed two-sided triple ideals. So this proof is extremely difficult, and although we were able to simplify the C-star algebra proof, the C-star algebra case proof, the TRO case still seems to be extremely difficult. But we will need the following lemma about tripotence in a real TRO. So tripotent is a partial isometry, i.e. Z is equal to Z, Z star Z. If Z plus minus B has norm less than 1 for an element in the ball, then B is forced to be of this form. So we'll need that because I wanted to just talk briefly about the proof of the M ideals in Jordan operator algebras result. So I guess they say that every talk should have one proof, maybe just to give a flavor of some of the ideas. But also, I think this proof is very interesting because it shows. I think it shows in a very interesting way how to adapt some of the complex techniques. In this case, some ideas of Smith and Ward from the 1970s, how to modify them and then overcome some of the complications that arise in the real case. So what are the complications that arise in the real case? Well, there's several complications which are, if you look at the paper, the two papers that I'm talking about today with Matt, Neal, Antonio, and Shan, the complications are pointed out in the introduction of these papers, but one of the complications when doing real versions of results about algebras, one of the typical complications is that there may not exist any Hermitian elements or any positive elements or any projections. So by Hermitian, I mean self-adjoint. Whereas Smith and Ward's first step is to show that if you hit the identity element in your algebra with the M projection, then that is Hermitian. And then they do a little bit of work and show that that is a projection. But this is not so easy for us. So I'll just mention. I'll go very quickly through the steps. And as I say, some of these paragraphs that I'm writing down are just coming from ideas of Smith and Ward. So effectively, in their paper, where they actually consider M ideals and M summands of complex Banach algebras, they basically have the following proof that if we let Z be P of 1, then for any state, phi of Z is the norm of P star of phi is positive. And this uses the fact that the dual of an M projection is an L projection. And because of that, we have this displayed equation at the bottom of the screen, which tells you that phi of Z is positive, and that's phi of, sorry, I don't quite know how, let me move that. And that's phi of P of 1, of course. So that's, yes. Okay. So for some reason, the arrows are no longer working. So again, I'm going to stop sharing for a moment. And I guess we can take this opportunity to have a short intermission, and while I share again, and just ask if any, are there any questions at this point? Okay, let's hearing none. Let's see if this. Yes, this seems to be working better. Okay, so I was at the bottom of that screen, and so the norm of 1 minus z is less than 1, and taking adjoints, we have this formula, and it follows that this element is positive. Now, so far this all makes sense in the complex and the real case, but for the next step, the next step would not make sense in the algebra in the real case, and so the trick here is now we have to move to the complexification. So I guess that's the key point of the modification of the proof in this case, is we move to the complexification now and write things in terms of we write our element Z in terms of elements in the complexification. These elements A and B, of course, do not exist in the original algebra. And if you take a state of phi of B with phi of Z equals 1, then its complexification is a state of the complexification. And then one could do some computations using the Cauchy-Schwarz inequality. I will just go very briefly through the rest of the slide. So we're using the Cauchy-Schwarz inequality in the fourth last line, and then we look at phi of Z star Z. So this again does not exist in the original algebra, but it's something we can consider in the complexification with this complexified state. and we obtain this identity in the second last displayed equation for z star z. We get a similar identity for zz star, and if you compare these two identities, you see that they only differ in this part here, and so that is very useful. That gives us that row of a squared plus b squared is 1, and I'll skip these computations, but eventually we get we write phi of z squared. Now this does make sense in your Jordan algebra, in your original Jordan algebra. We can write it as 1 plus I times the value of rho at ab plus ba. This, of course, is a complex number. But since phi of z squared is less than or equal to 1, because z is a contraction, and this element rho is in the real, this forces phi of z squared equals 1, and so phi of z times 1 minus z equals 1. So just to summarize, we've shown that phi of z times 1 minus z equals 1 for every state with phi of z equals 1, and can bootstrap from this to show that the same formula holds for any state, not necessarily with phi of z equals 1, or equivalently for the real part of every state on the complexification. So it's not hard to show that the states of the original Jordan algebra are just the real parts of states on the complexification. And here is the argument in the next two paragraphs. So I won't take the time to read through these paragraphs. But if you just stare at the screen, you can see there's nothing too troublesome that appears here. It's just some algebraic steps and checking values of norms, etc., to give you that phi of z 1 minus z equals 0 as claimed. So it follows that, I'm sorry, there's a typo here, follows that this identity, when you look at it in the complexification, is saying that the real part of the complexification of phi of rho of this element is 0 in the complexification, which shows that this element is skew symmetric. In other words, its adjoint is its negative, or d plus d star is 0. But d plus d star is just this quantity, and now a line of algebra shows that z is just a. Well, I'm sorry. If b is 0, then z is obviously a, and that is a projection from this identity, because a times 1 minus a is 0. That forces a to be a projection because it's also a contraction. So we've accomplished the first steps in the Smith-Ward proof, but it was a bit more difficult for us to do that. And then the next observation is something we're going to use the lemma that I had about TROs a few slides ago. If you look at P of x plus minus 1 minus z, then this is just P of x plus or minus 1 minus P of 1. And by one of the definitions I put up of an M ideal or an M projection, this is just the maximum of P of x and 1, which is 1. And so the lemma that I had up before the proof says that P of x is in ZAZ. Similarly, 1 minus P times A is in 1 minus Z, A1 minus Z. And the rest is just simple algebra. Since A is P of A plus 1 minus P of A, we can deduce that A is simply ZAZ plus 1 minus Z, A1 minus Z. And so Z is central in A. Another step of algebra shows that P is just multiplication by Z. So this, I guess, is as in the Smith, is very similar to as in the Smith-Ward proof. And so we have proof 2. We've characterized the M summands for unital Jordan algebras. And then how about M ideals? Well, it's usually the case that once you characterize the M summands, then the M ideals are usually an easy step from that. You just go to the bidual. If J was an M ideal, it's bidual, or it's weak star closure, or its second annihilator is just by the first part. It's just a projection E. That was my Z in the first part times the bidual, and this projection is central. I think I said that in the previous paragraph. The projection is central, so that is also the Jordan product of A and the bidual of A, and and so we know exactly what the bidual of our M ideal looks like, and so from that it is easy to see just by functional analysis that J is an ideal, respectively a Jordan ideal. That just follows by weak star continuity arguments, and J is approximately unital because its bidual is unital. And the converse is similar to this previous paragraph. So that is the main part of the proof of the theorem. Okay, so moving along, I think I have another 8 minutes or something. Is that correct? I would guess.
Yeah. Yeah.
I would guess that I should stop at 10:50. So in the last section, I will talk about Jordan operator algebras as operator spaces. So previously, we've been talking about them as Banach spaces. But to deal with one-sided ideals, and for everything else in the talk, we have to change perspective and talk about the operator space structure. So, and that's because there are two natural categories that Jordan operator algebras live in. The first category is if you consider them as Banach spaces with contractive Jordan morphisms. That's what we've been doing so far in the previous section. And the second category is if we consider them as operator spaces with completely contractive Jordan morphisms. So it's a fairly well accepted principle now in associative operator algebra theory that for many purposes, perhaps even most purposes, operator algebras should be treated as operator spaces. That is in the second category. And when I say operator algebras, I mean specifically non-self-adjoint operator algebras. Self-adjoint operator algebras usually, well, very often don't need to be treated as operator spaces, but of course, in that case, you still have the operator space thing going on. It's just a lot more automatic for self-adjoint algebras. For non-self-adjoint algebras, the operator space thing is not automatic, and so you really have to make that distinction. So you have to treat them in the second category. So for those of you who are not familiar with the operator space theory, I will just mention a few things. That a real or complex operator space can be, there are two ways of looking at it, either as a real or complex subspace of B of H for a real Hilbert space H. Sorry, this should say real, respectively complex Hilbert space, or abstractly as a vector space with a norm on the n by n matrices satisfying the conditions of Rowan's characterization. So Zhongjing Rowan had a very beautiful characterization of operator spaces, which is completely abstract. So there's no mention of the Hilbert space or any operator really. An operator space is simply a vector space X with a norm on the n by n matrices over X, satisfying the two Rowan conditions R1 and R2. The first says that the matrices over X is a normed bimodule over the matrices over your scalars. F here is the real or complex scalars. And secondly, that if you take the direct sum of two matrices, its norm is the maximum of the norm of x and the norm of y. So a beautiful, completely abstract characterization of operator spaces. Similarly, there is an abstract characterization of operator systems, which is what is an operator system? It's a self-adjoint subspace of B of H that contains the identity. And you can do this in the real case as well as in the complex case. In fact, last week, I think I put a paper on the archive, if you're interested, on which basically is a complete development of the theory of real operated systems, including the characterization, etc. But the morphisms in this category are bounded linear maps, except that they have to behave uniformly at every matrix level. So I think I need to speed up because I see I only have 3 minutes. So if you look at the map that just applies your map entry-wise in matrices, if that map is an isometry for every size of matrix, respectively a contraction or a positive map, we say that use a complete isometry, completely contracted, completely positive, and the completely bounded norm is the supremum of the norm of the nth, the map you apply to n by n matrices. And this theory of operator spaces and systems is a very large theory. As I said earlier, it's, I think, maybe one of the most interesting things I can say today is which other non-associative algebras can be treated as operator spaces and systems. So we, with in some of the papers that I mentioned earlier, we developed the theory of these Jordan operator algebras from an operator space point of view. So I'll just flash up some slides of giving some abstract operator space characterizations of Jordan operator algebras from papers with my students Genoa and Matt Neal. The first one is characterized in terms of unital operator spaces, which Matt and I had characterized abstractly, similarly to Ruan's theorem on a previous slide. So I won't read it. I won't take the time to read out the results, but there's one theorem. Here's a very different characterization in terms of the injective envelope. So the injective envelope of a unital Jordan algebra will be a C-star algebra, and the C-star algebra that it generates inside of it is called the C-star envelope. And so here's a characterization in terms of the injective envelope. There's a corollary. A corollary with an application to ranges of completely contractive projections. So I promised earlier that I would talk about the complexification. So the complexification is essentially uniquely defined in the second category, but not in the first category. So in the second category of operator spaces, Ruan proved that the unique matrix norms on the complexification, that is very important for us. Whereas in the first category, the complexification is not defined uniquely. You can find, for example, real unital operator algebras A and B with two quite different complexifications. Similarly, for Banach-Stone theorems, the very nice Banach-Stone-Caddison theorems for completely bounded maps, but not with contractive maps or isometries. That slide I just skipped through was talking about the unitization, and I see I'm out of time, so just very quickly let me skim through some slides here. So one advantage of treating Jordan operator algebras as operator spaces is they have a well-defined associative partial product. that you can do in a containing C-star algebra, but it turns out to be independent of the containing C-star algebra. And this allows us to talk about things like the left multiply algebra. And I have a couple of slides here from the paper that just got accepted about the left multiply algebra of a Jordan operator algebra. And I'll just end with the characterizations of one-sided M-summands, and I'll stop in just one moment. Sorry, going too fast on this section. Here is the definition of a complete left M projection of a right M summand or right M ideal. It's very similar to the definition of a two-sided M ideal. And here I'll just end with this theorem that if you have a real or complex approximate unital operator algebra or Jordan operator algebra in an idempotent linear map, then P is a left M projection if and only if it's left multiplication by projection in the multiply algebra, if and only if you have this nice norm condition. R2 stands for the rows, and of course from this you can characterize the right M ideals in an algebra as just being the right ideals with the left contractive approximate identity. And I think this may be a good place to stop. So I will stop sharing. And thank you very much.
Thank you. So I think this is a time for questions. Does anyone have a question? Yes?
Yes, I have one, if I'm allowed.
Yeah, you are.
Well, first of all, thank you for the talk, David. I really enjoyed it. Yes, this is a very general. I was just wondering by myself. I mean, you mentioned at the beginning of the talk the important connection between these results with the so-called non-commutative topology for several structures. Do you expect to have a stronger connection with those aspects of the theory?
Yeah, so I guess I really like those aspects of the theory. The non-commutative topology of Jordan operator algebras works out very beautifully, and so it builds on the very deep theory of Larry Brown, and so many connections that he had made between about the non-commutative topology of C-star algebras. So yeah, so the fact that this works for Jordan algebras, I think is very it worked out very beautifully, and it's very nice. It would be nice to see more applications. So you know, so some so in our paper we do have several
Yes.
applications, but it would be nice to see more applications, like for example using the non-commutative Eurozone lemma, for example, in some non-self-adjoint Jordan operator algebras to prove some nice results. That would be very nice. Of course, one thing that needs to be done is to just check that the real case of that, if the real case of that works. I suspect that it does, but I haven't thought about it too much.
Mm-hmm. Thank you. Yes. If anyone is also interested, maybe I could say that we also develop certain strategy to develop or to get certain non-commutative versions of this kind of results in the setting of purely general JV star triples, which is also an attractive setting from my point of view. It's pure geometry, probably even more geometric than this case. It is always
Definitely.
it is
Yeah.
always a big surprise that topology can returns you pure algebraic notion and vice versa. You can get geometry from topology. That is a nice applications in the
Yes,
results.
no, of course, I'm aware. I'm aware of your many wonderful papers on non-commutative topology and non-commutative Eurozone and various kinds of things in a JB star setting. That's yeah, it's very impressive. So yeah, I would love to collaborate again.
Okay, me too, me too. Thank you.
Yes.
So more questions or comments? Well, if not, I'm very thankful for your talk. Very, very nice talk and very inspiring because, well, it touched several points where that interest me, like
Mm,
non-commutative topology. I did a bit of it also in some years ago. And again, operator spaces that I worked on with Christian. So,
mhm.
and also JB star triples that I just heard right now. So it was very inspiring. Thank you.
Thank you so much. I hope to meet you in person sometime in
I hope
Europe, I
so.
hope, or in the States perhaps.
Yes, that would
And
be.
same for you, Antonio. We still have not met in person, so
Yes,
we have to change that. That'll be
yes, I'm willing to meet you in person soon. I hope so.
that'll be great. Okay.
So thanks
Thank
also to
you.
the organizers of this series of seminars and for providing some kind of good atmospheres for Jordan structures between analysis
Yes.
and algebra. We appreciate it.
Yeah.
Thanks
Yes.
a lot.
Thank you. Bye.
Bye.
Bye.